Wow. All set. Well, good evening to those that you could make it. Tonight, we're going to have a very interesting talk about the proposed and hopefully future uh, upgrades to what has been the very large array down in New Mexico. Now, I don't know how many of you have visited it. Oops, Dina says stop. Guess we're still working this. Give me a thumbs up when you're ready.
Okay, I muted myself because it was coming through twice. I think, though, what I need to do is mute it on YouTube. Just a moment. Aha, that's it. Yes. Okay, go ahead.
Yeah, I want to welcome everybody to the
Go ahead,
September
Dr.
INRI.
Bickle or Dr. Pesce. Go ahead.
Yeah, we are pleased to have as a guest speaker tonight Dr. Joe Pesce, and he will be talking about the proposed upgrade to what has been the VLA down in outside of Magdalena, New Mexico. With that, I will turn it over to Dr. Pesce. You have a slide presentation and you've got the floor.
Thank you very much. And so thank you for the intro, and let me start sharing. And there we go. Okay, so welcome everyone. Nice to see you all here. And I'm sorry I'm not there with you in person in Denver. But this is the next best thing, and it's great that we have the technology to be able to do this. So tonight I'm going to talk to you about what will hopefully be our new, eventually new radio astronomy observatory, the next generation very large array NGVLA, and we'll talk about the technology and what we might expect it to do. So first of all, many of you know me. I'm a longtime DAF member, even though I'm no longer in Colorado, sadly. But I just in a nutshell, I was an undergrad at the University of Colorado, and grateful for Van Natten scholarship support during my time there, and a physics major. And I did graduate school at Cambridge University in the United Kingdom. I've worked in academia, in the private sector. I founded and ran a small business, and in the government, and where I am currently at the National Science Foundation. And this would be, the NGVLA would be a National Science Foundation project. Currently, I'm the program officer responsible for the National Radio Astronomy Observatory, our federally funded research and development center that is responsible for operating and maintaining the very large array, the very long baseline array, and the North American portion of ALMA and Green Bank Observatory as well, and who are instrumental in designing and developing the NGVLA and eventually constructing it. My research background is in blazars, active galactic nuclei, so those things that host supermassive black hole that is feeding and producing lots of energy. And I'm on Instagram there if you're interested in following me. Haven't been very active recently, but I do occasionally post astronomy related reels and posts and whatnot. Okay, so let's first of all talk about radio astronomy very quickly. Again, another thumbnail sketch about what we're doing here in radio astronomy. And So we have a radio telescope, right, which is the equivalent of an optical telescope with the mirror. We have the dish that's collecting the photons coming in from the astronomical source at the top of the screen, reflecting off of the parabola of the dish, coming up to the secondary mirror, which I show here on the right, and then going down through various windows in what we call the front end. And then on the back end, I have the boxed region there on the back side of the antenna, where we have the receivers that take the photons, convert them into an electronic signal, and then shunt them off to wherever they need to go. And this image is one of the antennas of the very large array, as John said, in central New Mexico, about 90 miles southwest of Albuquerque. And this is an 88-foot diameter dish, 25-meter diameter dish. There are 27 antennas that work as an array, and we'll talk about that shortly. The secondary is shown up here on the upper right. Actually, this is one of the VLBA antennas in nearby Pytown, New Mexico, but they're practically identical to the VLA antennas. So here we are inside of the antenna, and this is the front end. You see various reflectors and windows and that sort of thing for the photon, the light coming from the secondary mirror. On the left here, I show you a top view of that, and these are the entrance apertures leading into the electronics on the back end. So behind the dish, and I have a picture here of one of the corners of that electronics cabinet. Not a large structure, but 4 or 5 people can kind of squeeze in there. And what we see is a couple of feed horns, the outside of which is basically these features on the left part of the image, and then the feed horn comes in, and again, the photons, the radio photons, are converted into electric signal. So in radio astronomy, in other parts of in other frequencies as well, and wavelengths, we can do this, but it's very difficult to do what I'm going to be talking about shortly. So in radio astronomy, we have 2 types of radio telescopes. We have the large single dish, or we have the single dish. This is a large one, the famous Green Bank telescope at the Green Bank Observatory in West Virginia, largest single dish movable antenna on Earth. In fact, it's the largest fully movable structure, mechanical structure on Earth, 100-meter diameter radio telescope. So it's a big light bucket, right? It's collecting a lot of photons, and it has great sensitivity because of that. So it can see very, very faint sources. On the other side of the field in radio astronomy, we can have an array or an interferometer. And here we see the VLA in compact configuration and in the famous Y orientation, our 27 antennas, observing the same astronomical object at the same time. And when this is done in this fashion, the array, the interferometer, simulates a single dish, single antenna that has the diameter of the most widely spaced elements of the array. And so we get the ability to see very fine detail on the sky. Just like in optical telescopes, the larger the mirror, the larger the antenna, the better resolution we get. But there's a trade-off with sensitivity. So we have that big single dish antenna at the Green Bank telescope, right? That's collecting a lot of photons. The very large array is simulating a radio telescope that is larger in diameter, but of course there's a lot of empty space there. So, photons come in and fall to the ground and are wasted. So we have a trade-off between exquisite resolution with an interferometer, lets us see nice detail on the astronomical target, but we lose sensitivity because we're losing, we don't have surface area. So these multiple elements, to work as an interferometer, the most important thing is that the data as they come in, the photons as they come in, have to be correlated. They have to be lined up in time, temporally, across all of the antennas. And in the radio part of the electromagnetic spectrum, it's a little bit easier, but still it's a difficult thing because we need to be able to differentiate time delays that are on the order of a nanosecond. And so the way we do this is, those photons come in the front end, they get converted into electronic signal in the back end, and then that signal is shunted off. But an atomic clock injects a time signal at the rate of once every nanosecond that then goes off to the exquisitely fast supercomputer that takes all of this information, that's called a correlator. The correlator then compares each antenna to every other antenna in the array and lines up all of those data streams such that we get that simulated single dish observation of the astronomical target. And again, the resolution is good because resolution scales linearly as the inverse of the baseline of the antenna. So the larger the separation of the individual antennas used in an array, the higher the resolution. And it's exactly the same for an optical telescope. The larger the mirror, or if we want to do an interferometer in the optical, the larger the separation between two mirrors, say, the higher the resolution on the sky. The problem as you go to higher frequencies and longer wavelengths, shorter wavelengths, so going into the visible, you need to have finer temporal resolution. And so a nanosecond is just about doable now, but if you get, you need to do it with more resolution in time when you get up into the visible part of the spectrum. And that's a very difficult thing to do. Most optical interferometers, in fact, use delay lines, so between the two elements or the multiple elements, so that they can delay the arrival of the photons as they're coming off the telescope. It's a difficult thing to do in the radio. It's exquisitely difficult thing to do in the optical. So we have done optical interferometry observations, but they're still kind of in the nascent stage, even though we've been working on this for decades now. It's still not quite there yet in the visible part of the electromagnetic spectrum, but it's done all the time in the radio because it's a little bit easier. Okay, so just a couple of points here. Astronomers in different wavelengths all do things slightly differently because the physics is different. In the radio part of the spectrum, this is almost more electrical engineering than astronomy. Obviously, it's astronomy, but there's a lot of electronics that are necessary to work with the photons. And the frequency range is very large compared to the visible part of the electromagnetic spectrum. And the physics of the incoming photons changes significantly throughout the range of the radio part of the electromagnetic spectrum, such that the devices that we use to convert the photons into electronic signal at different frequency ranges, the physics is different, and so the electronics are different. It's really quite a complex subfield of astronomy, primarily because of this. And by the way, in radio astronomy, radio astronomers use frequency rather than wavelength. They use wavelength as well, but frequency is what's used as opposed to wavelength in many other parts of electromagnetic spectrum, certainly in the visible part of the electromagnetic spectrum. So here we have our canonical schematic of the electromagnetic spectrum, and radio, and especially if you look down at the bottom, the radio part of the electromagnetic spectrum is just enormous, right? Many orders of magnitude, especially compared to the minuscule region of the visible part of the electromagnetic spectrum. And we are looking at frequencies and wavelengths that are millimeters and submillimeter and centimeters, and then as you go to lower frequencies, they get much longer, of course, meters and kilometers, and marked out where we have AM, FM, television, and the microwave part of the photons. Okay. I can't. People, if you'd like to ask questions, you may during the presentation. I have no problem with that. It's just that I can't see you. I've minimized all of you so I can see my screen. But you could also hold your questions until later if you'd like. Okay, so in the back end that I mentioned before, we have our receivers, and it's the receivers where all the magic is done, converting the photon into an electronic signal that can then go off to the correlator, the computer, and then eventually be observed by the astronomer and all of us. And I'm showing you an example of a receiver from the ALMA observatory in Chile. This is, I guess, about just under a meter, actually a little bit less than that, probably about half a meter. And the photons would be coming in from the top in this view. They'd go through all sorts of different optics here, and then they're converted as they go through the body of the receiver, converted into an electronic digital signal. And all of this, as with most radio observatories, certainly at ALMA, all of this is held within a dewar and chilled to between 2 and 4 degrees Kelvin, so 2 to 4 degrees above absolute zero. Why? Because the radio sources, the astronomical sources that we're observing in the radio part of the spectrum are typically very low temperature, and so we need to keep the noise in that conversion process as the photons are converted into a digital signal. We need to keep the noise to a minimum. So the technology in radio astronomy is used elsewhere outside of radio astronomy, for many uses. Our digital cell phones and all sorts of different things. The difference being that in radio astronomy, we are pulling signal out of the system that's a signal that's below the noise level. And cell phone technology, the signal is so strong that we don't really care about the noise. In radio astronomy, we care a lot about the noise. We need to keep it as low as possible. So that's why we're working with cryogenic temperatures. But there's also other aspects of the technology that go into this that keep that noise as low as possible. There are filters that are used in some of these systems, filters that are developed by the National Radio Astronomy Observatory, in fact, that are reflectionless. Because you have a filter in the visible part of the spectrum as well. Filters, of course, let certain light pass through, same way in the radio, but they also might reflect the light that they're not allowing to pass through. And that happens in the radio, but the problem is that adds to the noise. And so they have reflectionless filters that transmit what they need to and have no reflection whatsoever of the photons that are being rejected. And it's just amazing technology, and it's magical, the work that's being done. Most of that work is being done at the Central Development Laboratory in Charlottesville, Virginia, nearby the headquarters of the National Radio Astronomy Observatory. And of course, there's other places worldwide, but we're talking about NRAO here, and that's where all this work is being done. There's a bank of ALMA receivers, and here at ALMA there are 10 receivers, and you see 8 of them here inside of a dewar that is then an evacuated chamber and then chilled down to, like I say, 2 to 4 degrees Kelvin. But what I want to show here is that there are 8 receivers in this image, and you can see that the optics on each one of them is slightly different. Here we have a feed horn on the left. There's some mirrors over here on the upper right with a kind of a primary and a secondary, and another feed horn on the right that looks a little bit different, because again, the photons in different frequency bands that these receivers respond to are behaving differently. So the technology has to be different. The important component of an interferometer, of an array, is the correlator that I've mentioned. A very fast computer. In fact, the correlator at ALMA is or used to be one of the world's fastest supercomputers. But it's we can call it a dumb supercomputer, because all it's doing is multiplying and dividing. It's taking the signal from one antenna and multiplying it by all the other ones to correlate, to line up the signal, the timestamp, so that we can have again, a simulated single observation among all of those antennas. So it's doing a lot of operations per second, but it's not doing much more than, like I say, multiplication and division and addition and subtraction. Okay, so that's kind of radio astronomy in a nutshell. Let's look now at the next generation very large array, the NGVLA. So it's a project that's in design stage and in development, and it has been for the last 5 or 6 years, and that's been funded by the National Science Foundation to enable this project to be at a place in its life cycle such that if it's approved, then we can start construction without having to do the 5 or 6 or 7 or 8 years of design and development. We can do these sorts of things kind of in parallel, so that we can get a jump on being able to build this project. These are, big projects. They take a decade or more to construct, and so getting that development and design work mostly out of the way is a good thing, and that also allows us to reduce risk as much as possible. Risk adds cost, right? And so if we can reduce risk, then we potentially reduce the cost as well. So there's significant community buy-in, and NRAO has done a fantastic job in demonstrating the benefit of NGVLA to the community, to the astronomical community, not only the radio astronomy community, but the astronomical community in general. As part of this development phase, they've run a series of community workshops where the scientists can come in and discuss, what NGVLA will do for their science area, and those workshops also can be bootstrapped to provide input into the design of NGVLA, right? And so it's this cyclical nature of hearing from the community, getting buy-in, having the community tell us what they want to do with this, new instrument when it comes online, and then designing the instrument to be able to reflect that. So significant community buy-in. I've been to a number of these workshops, and what's really heartening is that they're demographically varied. They are among the most diverse astronomy conferences that I've ever experienced in my career, and there's a huge number of young scientists, which is a great thing. And as you would expect, it's the young scientists today are going to be mid-career when NGVLA comes online, more or less, and so they are going to be the users of the future. But it's very heartening to see that. The plan is that NGVLA will replace both the very large array that's currently operating, the 27 antennas in central New Mexico, and the very long baseline array, which is an array of 10 telescopes spread throughout the continental US. And I'll show you more about this shortly. It had strong endorsement by the Astro 2020 Decadal Survey. I'm sure you know about the Decadal Survey, but in astronomy, as in many other sciences, we convene every 10 years. And by we, I mean primarily NASA and NSF as the two primary funders of astronomy, federal government sponsored astronomy in the US. We sponsor these surveys. They're run by the National Academy of Sciences. And they go out, they solicit white papers from the community on the type of science that the community thinks should be done, on observatories that should come online, on instruments that should come online. And NGVLA was run through this process in the most recent decadal survey, and they gave a strong endorsement. And that's important for us as the federal government funding body to be able to point to that community telling us, hey, this is what we would like to do. So it's currently still under consideration. We have not yet started construction. It's being considered as part of this long process that vets the project, and then eventually the goal would be that yes, we will start funding it. Congress will provide funding. NSF will parse that out, and NRAO and partners will start construction. We're looking at $2.3 billion for construction. This would be, if it's approved, it will be the largest construction project that the National Science Foundation has ever undertaken. So this obviously adds some scrutiny as well. And we're looking at operational costs of about $93 million a year. And the expectation is that we will have partners, international partners primarily, providing some 25% of both construction and operational costs, as is necessary in with modern large-scale scientific instruments that are just too expensive for any one country to be able to fund. And so here's an image of the current design of the NGVLA antennas. I'll talk more about that just outside of the center of the VLA site in the plains of San Agustin in central New Mexico. Okay, so quick comparison here. On the left, we have the Very Large Array, the current existing observatory. There are 27 movable 25-meter antennas, with the largest baseline being 36 kilometers, and they can be moved into 4 different configurations. Again, the largest separation is 36 kilometers, and then going down to somewhat smaller array. Of course, that change in configuration gives us different resolution sizes, and frequency coverage of 1 to 50 gigahertz. On the flip side, the NGVLA is going to be comprised of 214 18-meter antennas with a 1,000 kilometer baseline. Again, these are stationary; they're not going to be movable. And then an additional 30 stationary antennas that are on a 9,000 kilometer baseline. And these are the replacement antennas for the VLBA, the Very Long Baseline Array. And we have about a factor of 2 larger frequency range coverage, 1.2 to 116 gigahertz. And if you care about wavelengths at this frequency range, it's 25 centimeters to 0.26 centimeters. Quick comparison with ALMA, not a complete comparison, but ALMA is operating in the millimeter part of the electromagnetic spectrum. NGVLA will be 10 times better sensitivity and 60 times larger baselines than ALMA. ALMA's largest baseline is 16 kilometers. So as we'll see right now, ALMA will be very complementary, highly complementary to NGVLA. So what I'm showing on the left, the y-axis here is basically a measure of sensitivity, and the salmon pink is NGVLA, and the purple shaded light and dark is the square kilometer array that's under construction in Africa at the moment, an international consortium of the UK, Africa, South Africa, and Australia, and a few others. And that will be coming online kind of on the same time scale, a little bit sooner than NGVLA. And then we have at the bottom there in red, I guess, is the current VLA, and on the right, past that atmospheric absorption gap there in bluish is ALMA. So we see that NGVLA has greater sensitivity than both ALMA and the VLA and SKA, of course, because there are more antennas. So just to give you an example, the ratio between VLA and NGVLA here means that at a given frequency, NGVLA's exposure times are 100 times shorter than the VLA. And again, that's just because, you know, of the huge number of antennas that they're going to have. On the right, we see as a function of frequency the angular resolution available to various instruments. So NGVLA, again in this salmon pink, you know, going down to exquisitely high resolution because of those very long baselines, and the square kilometer array, current VLA, ALMA in the middle here, and then our optical and infrared telescopes on the right side there. And this horizontal line that I'm pointing out here is the resolution, the size of 1 astronomical unit at 140 parsecs. And so this is chosen because it allows us to observe a number of star-forming regions, you know, in our galaxy nearby the solar system, and so NGVLA would be able to see down to 1, actually better than 1 astronomical unit at that distance, and that's just at the level of the European Extremely Large Telescope in the optical. So what we're seeing here is that NGVLA is a great complement to ALMA in the millimeter and to the square kilometer array. And so these are going to be the workhorse interferometric radio telescopes in the 2030s. And they will do great science among all of them. Okay, so those 214 and 30 and plus 30, we have 244 18-meter dishes, and there's a short baseline array of 19 antennas that are 6 meters in diameter. All of the antennas can be operated as a single array, so a single telescope, or they can be subarrayed. And so, you know, components can be observing different astronomical objects, or different components can be used to look at different resolutions of the same astronomical target. We see that the majority of them, 214, are going to be in the desert Southwest, mostly New Mexico, but going into Arizona, Texas, and down into Mexico, currently northern Mexico, although Mexico may add antennas, and centered on the current VLA site. So in the upper left, you see that there, the circle that's drawn is centered on the VLA site. And then if I go down to the bottom left, I've zoomed in, and now I'm looking at the VLA site. The dense concentration in the middle, and I have more of a blow up on this in upcoming slides, is basically where the current VLA antennas are. And then these spirals come out into the plane of San Agustin and then continue out into Texas, Arizona, and Mexico. On the right, you see that in the desert Southwest, of course, and in red, and then with the blue dots spread throughout the continental US, in the Caribbean here on the right, and Hawaii on the left. Those are the sites of the current very long baseline array. There are 10 antennas currently from the VLBA. There will be, for each one of those, there'll be 3 antennas at the VLBA sites, decommissioning the current VLBA antennas. And so that forms part of the so-called long baseline array that has that 9,000 kilometer baseline between them. And so all of these, all the antennas can work together, again, as a single radio telescope. The resolution I want to point out here. So the main array, that 1,000 kilometer here in the desert Southwest, depending on the frequency, because resolution is frequency dependent, of course, we get between 0.5 and 50 milliarc seconds for that shorter 1,000 kilometer main array. And then for the long baseline, that 9,000 kilometer array, we have between 60 micro arc seconds and 6 milliarc seconds. So again, just phenomenal resolution here on the sky. Again, just a blow up of this, showing the whole array from Hawaii to the Caribbean, and then down in from Canada in the north and down into Mexico in the south. Showing again the plains of San Augustine, the current VLA site, and again, current VLA is centered on this spiral. And so it's some 60, I want to say 60%. Don't quote me. It's about 60% of the antennas, of the 244 antennas, are within the current plains of San Augustine. So the vast majority of them will be there. And then if I zoom in, this is the current VLA site, the core. You see a large number of antennas, and then this little short baseline array with the 6-meter antennas there. Okay, the antennas themselves are fantastic. They are a great design, and they will almost certainly be used in radio astronomy and elsewhere, whether NGVLA becomes a project or not. So these antennas have been designed, and they are currently, one is currently being manufactured as a prototype. In fact, it's being finalized by fantastic German partner company called MTech in Leipzig, Germany, and Spain. They're creating both the antenna and the support structure and the pedestals, and they are completing that in the next couple of weeks. They should be, and then packing it up for shipment out to New Mexico, where it should arrive in January, and then the prototype will undergo a year of testing, both from a mechanical perspective and from the astronomical perspective, and then tweaked, presumably, slightly, and then we'll go into full production once construction has been approved. And the design is such that it has this offset Gregorian. So it's a significantly different design than the very large array antennas that we saw before. And the reason for this is that secondary is low, so that when the telescope is stowed in this position, the secondary and equipment here can be accessed by 2 people and a pickup truck, because the maintenance of these antennas need to be kept to a minimum, right? Number one, there's a huge number of them, and number two, they're spread all over the place, and so they're not movable, so we can't bring them back to the barn like the VLA antennas can be. They have to be worked on site, and they can't have the maintenance. How do I want to say it? They can't require the maintenance that the VLA antennas currently do, because the operations cost would be astronomical, no pun intended, if that were the case. So these antennas are designed to minimize maintenance to the extent possible. So we have the low feed arm. The pedestal is a concept that reduces life cycle costs because of the structure for moving the antennas. The drives, the motor gearbox, and that sort of thing, they're all designed for to keep maintenance to a minimum. And the materials on the antenna are cast and then post-machined aluminum for the panels, with a steel backing and composite sub-reflector here on the left, and mostly carbon fiber in the feed arms. So these are big. I saw some samples when we had our design review last December in Germany, and these feed arms are spun carbon fiber, and they're meters long. It's just amazing the technology that's gone into producing these things. They're 18 meters in diameter, offset Gregorian, with shaped optics on the panels. The slew rate is 4 degrees in 10 seconds, so relatively quickly, and with a surface figure of 160 microns root mean square in the figuring. Now, I haven't seen the latest numbers from the prototype, but in testing, they were able to reduce that to about half that requirement. So again, these are going to be phenomenally nice antennas. There's the view of it pointing skyward, and you can get an idea of the scale with the truck there. And here is the view looking face on the antenna, and there's your 18-meter diameter surface. There are 66 panels. We see 66 panels that are all slightly different, and so they're machined to the shape that's necessary, and then bolted into place. And here's one of them. This is a proof of concept antenna that was presented at the design review last December in Frankfurt. And just you can see how big they are. Again, there are 66 of them, and there's on the bottom left, you can just kind of see the curvature there. So these are again, they're reflectors, and so they're not flat, and that's all machined aluminum. Okay, the receivers, there will be 6 bands to cover that frequency range from 1.2 to 116 gigahertz, and that will be serviced by divided into 6 bands in 2 dewars. Again, these are cryogenically cooled, just like all receivers in radio astronomy, and they will be 2 dewars, one for band A on that lower frequency, and then the higher frequencies in the second dewar. And you see the notional design on the right side. So there's new technology going in here. A lot of it is technology that exists or just needs to be tweaked slightly. This is a cost reduction, of course, but there are some technologies that are under development. And the correlator, for example, will the requirements for the correlator are unlike anything that we've had before, used before. We're looking at 60 petaflops per second. So it's like a Frontera-like machine, Frontera being one of the fastest, I think it's still the fastest supercomputer on Earth. The cryo coolers that will be used to cryogenically cool the receivers and their dewars. NRAO is looking at a Stirling engine design such that there's no or very few moving parts. And the reason for this is, again, to reduce maintenance. The cryocoolers are currently one of the pieces that requires a lot of maintenance on radio telescopes in the VLA, for example. And so, we want to reduce that maintenance requirement on the 244 antennas and times 2, right? The multiple doers on each antenna. And so there's this Stirling engine technology that's still under development, but is very promising. And number one, it's optimized for efficiency. On the right side, you see that using the Stirling cryocooler instead of a current cryocooler reduces the energy, the power requirement by 580 kilowatts across the entire NGVLA. It uses a small amount of helium and is almost leak-proof. And helium is a non-renewable resource, and so that's really important, hydrocarbon-free operation. So this is a really exciting project, but it just shows that some of the technology is still under development. And then, there's huge power requirements for the entire array, 6.5 megawatts necessary to run the array. So we're looking at solar and wind to offset some of those power requirements. Wouldn't be able to offset all of it, I don't believe. Okay. I haven't been watching the time, and I'm running late. So let me very quickly go through the kind of science that we're looking at here. There are 5 key science goals that have been enumerated for NGVLA as kind of their main workhorse activities. And most of astronomy kind of fits into this, but there's a lot of astronomy that doesn't fit into these. And it's important to note that we're not saying that, I'm not saying that NGVLA is only going to be doing these 5 things. It's going to be doing everything. But these are the key main reasons for why we have this big new telescope. So, unveiling the formation of the solar system analogs. And, ALMA can look at that protoplanetary disk kind of on the scale of, way out into the Kuiper belt and beyond. NGVLA can zoom in, and on the bottom left there, you see a simulated protoplanetary nebula. The bar is 1 AU, and Uranus, Saturn, Jupiter, and Neptune locations are marked. So, we'll be able to look at the large scales with ALMA and then drill in with the NGVLA. You see the planetary masses and the semi-major axis in the middle here, using multiple different observatories and instruments to observe, and you can see how ALMA gets us way down into this region of planetary mass and semi-major axis. On the right is a simulation of a Jupiter mass planet, the dot in the middle of these 3 that I'm pointing at 5 astronomical units. So, at the location of Jupiter. And what we see leading and trailing are the L4 and the L5 Lagrangian points. So, dust that's in those Lagrangian points. But want to point out that number 1, NGVLA can make this observation, and number 2, this is a simulated image such that we'll be able to see videos of this sort of astronomical target. And so that's, that will be new and really quite exciting. Let me show you these little videos that have been put together by the team. The text is on the bottom explaining what's going on. There's no sound, and they're 10 seconds each, so we shouldn't take too long here. But again, this is the goal of studying solar system analogs, so we understand our solar system better, and of course exoplanets, how exoplanets form. Okay, key science area number 2 is probing the initial conditions for planetary systems and life with astrochemistry. So, where looking at the molecules that are in protoplanetary nebula, complex molecules. There's lots of complex molecules in the interstellar medium and in protoplanetary nebulas. And NGVLA will do a great job with these. And the point here is that a lot of these molecules are chiral. They come in left and right-handed varieties on Earth. There's a certain type of chirality, and is that ubiquitous in protoplanetary nebulas? What's going on? And so NGVLA will be able to study this sort of molecular astrophysics. Here's an example of a spectrum of molecules that you see along the bottom here. And current observatories like GBT aren't able to get to the sensitivity necessary to be able to detect these molecules, but NGVLA will. Okay, so charting the assembly, structure, and evolution of galaxies over cosmic time. So both nearby and very distant galaxies with their supermassive black holes to understand how the galaxy and the black holes are working together and changing over time. A key open question is, how does the supermassive black hole affect the galaxy? And it's not affecting the galaxy because it's sucking stuff in, because it's down in the very center of the galaxy. It's affecting the galaxy when it's an active nucleus, because it's producing a wind that's potentially blowing away the interstellar medium and then stopping star formation. So how does this change over time? And what is the feedback between the black hole and the galaxy? And how does that affect the evolution and star formation? So again, NGVLA will be able to go in and conduct surveys of molecular gas in the interstellar medium and observe the gas in the interstellar medium and then compare how is it affected by the supermassive black hole. Okay, using pulsars in our galactic center as fundamental tests of gravity. So in the very center of the galaxy, some models indicate that there are thousands of pulsars. We haven't detected many, if any, and so there may be issues here, right? But NGVLA will tell us. We'll be able to detect these pulsars if they exist, and if they don't, then that's interesting as well. So number one, detecting them is important, but then number two, using them as a probe to test relativity in a region of extreme gravity around the supermassive black hole in our galaxy. And we'll be able to test theory of relativity in unprecedented ways using this method. Okay. And key science area number 5 is understanding formation, evolution of stellar and supermassive black holes in the era of multi-messenger astronomy. So what is multi-messenger astronomy? It's all the messengers other than, it's all the messengers, photons from the electromagnetic realm, gravitational waves from the gravitational realm, and particles. And so NGVLA will allow us to understand stellar and supermassive black holes as the producers of gravitational waves. And so observations in conjunction with LIGO, our gravitational wave observatories, and international efforts in gravitational waves detection that will be coming online in the future. So this is using the electromagnetic messenger to help us understand the other messengers as well. Okay, because gravitational wave observations are really now coming to the forefront of starting to become old hats in astronomy, and yet there's most of what's going on in the gravitational realm is really not well understood because it's a new area, it's a new window in astronomy, and so NGVLA will help with that. Okay, so timeline. If all goes well and construction is approved, it can start as soon as 2026 and be completed by 2035. I suspect that will slip, but nonetheless, that's the notional timeline. And those antennas are being constructed. There'll be multiple antennas constructed per month to be able to get this timeline and to complete in this time frame. So at some point, we'll have a critical mass of antennas, and so that's why we expect to be able to start science observations in 2028. Not with a full array, of course, because it's still under construction for another 7 years, but with some sub component of that. So that's really quite promising, and this is a great schedule if we're able to start on time in 2026. Okay, so I'm going to stop there. And I have a couple of minutes for questions, if there are any.
Comment. It's nice to see the use of the offset Gregorian design in the antennas. You mentioned the fact that design will facilitate some simplified maintenance, access, and reduce maintenance costs. There's another benefit to an offset feed antenna like that, and that is better performance and efficiency.
Yeah.
The VLA antennas are traditional Cassegrain designs that have struts holding up the subreflector, and then of course there's the main feed horn down directly beneath that. And if you imagine that you're a radio wave coming in directly to that type of antenna, what do you see as you look at that dish? Well, there's the subreflector supported by those struts, and they're effectively blocking part of the radio signal and scattering it, and also potentially allowing signals coming in from other directions, undesired directions, to bounce off of those struts and so on. So, I mean, they work fine, they work okay, but how do you improve that? Well, you improve that by taking a segment out of a parabola and mounting the feed at the bottom. So if you visualize this being the reflector and the feed down here at the bottom, the main bore side of the dish is not straight in like this, but it's at a higher angle like this, and it bounces up to here. This reflector, or sorry, this feed point is not in the path of the target signal being received. It's coming in at a higher angle. So the radio waves coming in see the reflector surface, the primary reflector. They don't see this down here. And so that's a big enhancement to performance and efficiency of the antenna system. So that is really cool that that's being used.
Yeah, absolutely. And I should have pointed out as well. Thank you for that. That's great. The receivers there are on that second, right? It's not so you increase efficiency as well. You're not having multiple bounces as you go through. But yeah, absolutely. That's fantastic.
Kind of like the old prime focus backyard satellite dishes. So they still had the struts, but the receiver, or in that case the LNA, the low noise amplifier, and the block converter was inside at the feed point.
Yes.
So you didn't have the reflector. So you gain efficiencies by doing that. That is really cool.
Yeah, and they're really well designed, and well, it's going to be exciting to see one of these antennas in January down at the VLA site. There's a pad that's ready to accept it, but the MTech, the German company, has done a fantastic job on them, and it's really kind of neat.
The surface accuracy you described is pretty impressive, and you said it was coming in at about half of, I think, what was anticipated. So that's really nice. That helps the performance, especially at the much higher frequencies.
Yep, absolutely. Mark, I see Mark's hand up.
Where is this Stirling engine coming from? That's incredible performance to get down to 2 to 4 Kelvin, and with almost no moving parts. Where is that coming from?
Well, the Stirling engine concept is a 19th century technology, but so it's been it's being adapted. It's only on paper at the moment, and so the thought is that Stirling engines are in use here and there, but not substantially, because they've been a little bit more difficult to design and develop historically. And so you just use the old-fashioned vacuum pumps and cryo coolers, and you have multiple stage cryo coolers, and using helium, you get them down to the temperatures that you need. But again, they require a lot of maintenance. They're leaky. They leak a lot of helium, and when you have them 50 feet from maintenance shop, that's great. It's easy to deal with. When you don't, you need something better. And so NRAO thought, let's see if we can make the Stirling engine work. And it appears, at least on paper, it appears that it's a good design. They're still in the process of developing that. That's one of the things that it needs a little bit longer lead time, but we're hopeful that we'll start to construct some prototypes in a year or two, I think, with the Stirling engine. Yeah, they're neat, and they can be sealed, right? So they're sealed. The helium is, there is some leakage of helium, but it's minuscule compared to current technology. And what's neat is that, right, cryo coolers are everywhere in society. Go to your medical imaging facility, and there's dozens, if not hundreds, of cryo coolers. And we're hopeful that once this design is in place, we can use it in other areas as well. There's interdisciplinary activities that can be here, and the expectation is that the medical imaging industry will be clamoring for these as soon as they're available. There's been some initial forays by NRAO to talk to people who are using cryo coolers elsewhere, and they're really quite intrigued and kind of waiting with bated breath for this technology to come out. So yeah, it'll be neat. Fingers crossed that we can make it happen.
Yeah, thank you.
Got a question. You mentioned early on the use of reflectionless filters. That brought to mind, at least in the world of microwave transfer. I used to do microwave link and path engineering and testing and so on way back up in the 13 gigahertz range, and circulators were commonly used to improve the return loss performance of waveguide structures. And I'm curious if those reflectionless filters are taking advantage of circulator technology.
I don't think so. I don't think so. I think it's a material.
Okay.
So it's at the material science level that it's. It's almost black magic, some of the stuff that they're doing down there in Charlottesville, but I don't think they're doing using circulators.
Got my curiosity up now.
I don't know if there's. I think they just mentioned reflectionless filters. There may be literature out there. There should be. I think they have a patent on, at least I'm sure they have patents on reflectionless filters. There should be literature out there if you're interested. I don't think anything is on the NRAO website though. They mention them, but it's just kind of in passing.
Huh.
My question is, how are the signals from all these antennas being transmitted to the correlator? Because typically a very small array and a very large array have to use totally different methods, and you've got both here.
Fiber optics. So the
fiber optic across the whole country.
Yeah.
Wow.
So the VLBA has historically used data tapes, cassettes. So they make their observation, and then monthly or whatever, they ship them back to Socorro, New Mexico, where the VLBA correlator is. A couple of years ago, we we got some extra funding from Congress, and we were able to fiber all of them, but not at high speed. So we can do some controlling through the fiber optic system to the VLBA, but some of them are at high speed, 100 gigabits per second, but most of them are at 10, I believe. So we can't do exfiltration of data yet from the VLBA, but the NGVLA will have the high-speed fiber links. And the VLBA fibering was mostly tapping into trunk lines that weren't too far away. Some of them, they had trunk lines that were within 50 meters. Others, we had to go several kilometers. But in those 10 locations across the continental US and Caribbean and Hawaii, we were able to tap into existing fiber trunk lines. And expectation is that NGVLA will be the same. I don't think we're expecting to have to run fiber on our own, and that would be horrendously expensive.
Thank you.
Now,
I think the good news is there's optical fiber cables all over the country now.
Yeah.
Telecom companies and cable companies and others have, even the railroads and stuff have installed fiber all over the place. And almost any place there's a railroad track these days, there's a fiber optic cable buried in the right of way. Same with major highways, and so fiber's everywhere. And it's a matter probably of building a few short spurs to get to some of the antennas from the,
exactly.
from the main backbones.
And they're optimizing locations. So those locations that you saw on the spirals, the location is pretty important, but they have 30 to 50 kilometer wiggle room. So if they went and said, hey, we want it over here, and realize, hey, that's 150 meters from a fiber drop, the fiber trunk line, they can move that a little bit to do that. So they're a little bit flexible in that. Not only fiber, but other things. They can move their locations around. What did I want to say? Oh, so there's a tremendous amount of data at the telescope, at each antenna, far more than could be transmitted. The good thing is that the vast majority of that can be thrown away before it gets sent off on the fiber line. So a lot of the incoming, once it's digitized, a lot of that signal, a lot of that digitized information is not important, and so it's jettisoned, and then only a small subset is sent down the fiber lines.
Oh,
Anything else?
well, that was fantastic.
Well, thank you.
Yes.
It's a fantastic.
I felt like, I don't know, I personally felt like we were drinking from a fire hose here.
There's a lot there, yes, and I apologize for that, but it's an amazing thing, and I just had the thought, can we do this? Well, you should all go visit the VLA. Number one, because it's a nice place to visit if you haven't been there. Number two, it may not, as it exists now, it's not going to exist forever. I think we're still thinking about what to do, but we're not going to keep all 27 antennas. That's certainly the case. We'll probably, have one. But so you have some time, but number one, there's that. Number two, I'm trying to think if the NGVLA antenna will be visible from, I think you might be able to see it. You won't be able to go to it, but you'll be able to see it on its pad from most of the places that you can get to as you're doing your tour of the VLA. So that should be there from January. Fingers crossed. I've not heard of any slips or anything, but we are in September, and they should be shipping in a couple of weeks. So I'm looking forward to that. But yeah, it's a fantastic instrument. Keep your eyes open. I should point out, let me do this here in the chat. It's ngvla.nrao.edu, I believe is the website, is the public-facing NRAO website for the NGVLA project. And there's some additional information in there too. Dina.
So
If you go down there to the VLA, they give you this cool lapel pin too.
Oh, there you go.
I didn't get that when I went last year, but the visitor center wasn't technically open. So we got a special visit, but we didn't get to go indoors. Um, now the old VLA, if I get this right, they did some version of transmit and then receive, right?
So we've done radar tests
Uh-huh.
and was in the past, there have been radar tests from Arecibo. So Arecibo transmitting and VLA receiving.
Okay, that was how that worked.
More recently, and you can poke around for that too, there's a prototype radar transmitter and radar system that's being tested and had been tested at the Green Bank telescope. So using the big single dish Green Bank telescope as a transmitter, and then the VLA, and actually more importantly, the VLBA was used as in receive mode. And NRAO along with Raytheon, we're doing some tests, and there's the results of those tests from the moon are out in the public domain. I could probably poke that up, but if you search NRAO moon radar test, you'll find it, and it's really quite amazing. The images of the moon are the highest resolution radar images of an astronomical target that have ever been conducted, and that was using a 700-watt transmitter, so something the size of a microwave oven.
Wow.
There are plans to possibly put a large high power radar transmitter, and it would have to be on Green Bank, some big telescope, and then picked up by VLBA to get the resolution. But there's an expectation that NGVLA could be used this way as well, either as a subarray or the entire array or whatever. So that'll potentially have great uses in the radar. Of course, I didn't talk about that.
Of course, with 700 watts of
That's what I was wondering about, was if it was going to be used for any radar reception at all.
Possibly, yes. There's no reason why it couldn't.
The use of a 700-watt transmitter may sound like not very much power, but keep in mind the gain of that Green Bank antenna, and depending on the frequency, the effective radiated power from that thing has got to be in the megawatts range.
Yes.
Right. Well, and the signal we're getting back from the Voyager spacecraft, it's so teeny, tiny, but it requires a collector like this to be able to receive it. So yeah. Wonderful. Well, thank you. I appreciate this. This has been amazing.
Well, thank you for having me. Thank you. I appreciate your interest.
Thanks again, Joe.
Thanks,
Any
John.
other questions from the other observers here? I guess hearing none. Well, thank you very much, and we will close the thing. And I guess, Dina, we shut off the live feed at this point.
Will do.
And
Stopping the-
I guess how do we